Okay, in our last video, we discovered that the electrical energy between two charged objects can be found using this equation, which is very similar to the energy for gravity. Don't square the r. The only difference being that this one could be a plus or a minus. We don't really have a particular case where it's always going to be minus, and that's because electricity has both attraction and repulsion, whereas gravity only has attraction. All right. Now, we have another way of expressing this. We can express this using what's called the gravitational field constant, right? And so before, we took the electrical field constant, E, and we found that it was equal to K, and then Qm, the charge that's making the field, over R squared. This one is squared, remember, because this comes from the force equation. And we found that we could use F E equals K Q1 Q2 over R squared, or we could use FE equals QE, where E stands for these three numbers. The only difference is that E doesn't have a nice easy number every time, like 9.8. You have to calculate it every time using K and the charge and the R. So it's not as simple, right? But again, this is electrical fields and these are forces. Okay, at the end of the last video, what I did is I said, what if we could take this energy equation and produce a constant electric field? Well, if we could make a constant electric field that never changed, then that means that the E number right here is always going to be the same. In other words, these don't change right here. So it's similar to what we did with gravity. If the Earth's mass doesn't change and you're always near the surface. If that were the case, we could then take the equation for energy and we could say that energy, electrical, equals the force electrical times the distance that you would move, right? Force times distance. So just like gravity is force of gravity times distance, force of gravity was mg and then distance was h. Here, what we do is we say QE moved a certain distance d. But of course, this all depends on a constant E, a constant field strength. Just like this mgh only worked with 9.8 for g. You couldn't use some satellite that was further away because g didn't work, and so this was a shortcut for constant g at the Earth's surface, and this is a shortcut for constant field strength. Now, we're going to talk about how we can get a constant field strength first. In your textbook, they do this near the end, but I think it's important for us to understand. This does not work between two objects like this, and if you move this one away. And the reason it doesn't work is because as you move it away, you're changing the R. And if you're changing the R, then you're changing this, which means the E is not constant. So this equation only works if you could somehow generate a constant electric field. How do you do that? Well, there is a way. The way to do it is to take a plate, a conductive metal plate, along with a second conductive metal plate, and then connect them to a power source, like this. Now remember, with our power sources, this is the negative side and this is the positive side of the cells that are creating this push, this voltage, right, between the two. So what happens here is we imagine that this creates a positive plate, and this creates a negatively charged plate. Now the electrons are sort of being pushed towards the negative plate, and they would like to complete the circuit and get across, but they can't. Now what happens if I place a little charge that's positive right here? What will happen to it? Well, it'll be repelled from the positive plate and attracted to the negative plate. And so it'll feel a force across this way. And if you think about it, it doesn't really matter where it is. If I put it here, it'll feel the exact same force because it'll feel a little bit less repulsion from the plus because it's further away, but it'll feel more attraction from the minus because it's closer. And that'll still work out to the same number. So what we get is a field between these plates that goes across, and it doesn't matter where you put your charge, it will always feel the exact same field strength. We get a constant field strength between the plates. And we call this the parallel plate apparatus. It actually has a name. Now, the trick is that by making this in a lab with two metal plates, you can produce this, but you can produce the same effect anywhere where you have charge distributed the same sort of way. Okay? So it doesn't have to be two metal plates. It could be any conductive material. And for instance, when you get lightning, you get a cloud. And what happens is the ground, the cloud develops charge imbalance. So what happens is negative charges tend to accumulate near the bottom and positive charges near the top. And that's because what's causing that separation is the friction and the movement of air currents pushing on the charged droplets, right? And then what happens is on the ground, there's positive and negative because the ground is neutral. But this negative charge on the cloud repels away the negative charges from this region, pushes them to one side. So what you get is a cloud on top with a negative region near its bottom, and in the ground you get the positive, and all the electrons or all the negative charges have been sort of pushed or scared off to the sides. They're still there, but they're pushed away. And now, because remember, you can move electrons, but you can't move protons. You can't move positive charge. So you scare away the electrons, and now you've created two plates, a negative and a positive plate. And of course, lightning comes down and flashes to the ground as the electrons try to break through the air. But before the electricity strike, before the lightning, what exists between these two and what causes the lightning to work its way is a field. And there's a, whoops, still got the eraser on. Better put my cloud back. Oh, pen, here we go. What we get here is a constant, relatively constant field of positive charge movement this way. Remember that fields are always the way positive charge would move. And so the Earth and the cloud are acting like parallel plates. So it doesn't have to be two metal plates, but we use this as sort of the apparatus to describe it. And so in this case, between two parallel plates, with this constant E, then you could use the equation of work or energy, electrical work or electrical energy, it doesn't really matter, both are the same, QED. And what this would mean is if I took a positive charge and dropped it in here, it would shoot along those force lines, right? Those field lines. But if I put a positive charge here and I wanted to push it this way against the field and move it a certain distance d, I would need to apply the force QE to move it and the distance d. So there's the QED. So this equation can tell us things about how much force is required to move it or what the electric field strength would be and so on. So this is a situation where we can get a constant electric field. All right. So now that you know that, and we'll come back to that later, we're going to talk about, we're going to make the assumption that we're always dealing now with a constant electric field. And we're going to make a comparison. Right? Okay. With gravity, let's say we had an object and we wanted to lift it up from here. Well, we would move it up a certain h. Okay, and as we said, we would apply the force mg. That you'd have to apply a force equal to its weight, or the force of gravity pulling it down. And so it's fg multiplied by the height that we want to move it, so that became mgh, and that represented the work that was being done. And now with gravity, or with now. Okay, what I should point out here is that this h, technically, the little value of g here is not the same as the little value of g here, but because it's changed so slightly. Remember, the value of g is based on the surface of the Earth. Well, if you move something 6 meters, that's nothing, which means we can arguably say that the value of g is relatively constant over small heights, right? Even though we know it's technically not, it's so close. We can say that it's relatively constant over small changes in height, and we can use this equation as a shortcut. And this, by the same token, if you want to move something in a field, if you want to move a positive charge, and you have a field that's pushing downwards, so your field is this way, just like gravity, right? There's your E pushing down. Then you need to apply a force up. That's the electrical force you would have to apply, and that would be the force electrical times, you could call it an H, or the distance you want to move it, and that's the QED. And so that's how you calculate work or energy changes in constant electric fields. Okay? Good. So now we have two equations, and I'm going to summarize them all at the end. We're going to do another video with a summary of electrical formulas. What's hard about electricity is it's all the same concepts you did with gravity, but it's all different letters and different things that you're not accustomed to using because we never did this in grade 11 at all. So it's all different things, and that's what the hardest part of electricity is getting your head around what's the Q, what's the E, what's the D, and the only way to do that is to study it, right? To study it to death. Okay, there's another thing we like to use in electricity that we could use in gravity, but we really don't use it very often. Okay, so let's say you go to the store and you want to buy flour or sugar. Let's say sugar. Okay, when you go to the store, especially if you go to the bulk barn, let's pretend we're going to the bulk barn, right? When you go, so the bulk barn, and we're going to call this Metro. So when you go to Metro, the sugar comes in a big bag. You can get a 5 kilogram bag or a 2 kilogram bag, right? But that's about it. If you look really hard, you might be able to find the little packets for coffee, but that's even harder to find. In other words, and they'll give you a price. They'll say this 5 kilogram bag is $7, and the 2 kilogram bag is $3.50. And you buy 12 of these or whatever, but we won't worry about those. Okay, you go to the bulk barn though, you can get any size you want. You can get 1 kilogram, you can get half a kilogram, because you're just shoveling it out of the box. There's no standard mass that you can get. So how do you know what the price is? You can't say it's $7 or $3.50. The only thing you can do is give people the price per kilogram. Which means you pick whatever number of kilograms you want, you apply this price per kilogram, and that'll tell you how much you owe. So they will say it's, $1.50 per kilogram. And that's more useful at the bulk barn because then you just take you weigh it out, right? And away you go, multiply by 150. With electricity, it's quite common to do this same sort of thing. For instance, we might say, okay, let's say we have an electric field going like this. E, electric field. And I want to move something, or I want to push something, and I want to put it right here. And I want to try to push it up against the field. That means I have to apply a force, right? Okay. Now, I could figure this out by doing F equals QE, right? So I could say that the force applied is QE. But perhaps I don't really know how much of a positive charge there is. Just like at the bulk barn, that positive charge could be anything. So what I might want to know is not so much the energy in terms of, so let's say we did electrical energy, right? And I could go QED, force times distance, so I'm going to move it this distance D. what if I just wanted to know the price per kilogram? In other words, how many joules of energy are necessary, right? Or are going to have to be added to change the position of this positive charge this much. So the price per charge, I want, instead of price per kilogram, I want joules per charge. So then I know, if I know it's 10 joules per coulomb of charge, then whatever the coulombs are for that electric charge, I just multiply by 10. So it's kind of like doing the bulk barn thing. And we have a name for this. We call it the voltage. That's what voltage actually is. It's not exactly energy, although in grade 9 you might have been told it is energy, or it's the same thing. It's actually the energy per charge. So voltage is actually measured in joules per coulomb. Whoops, better spell coulomb right. Joules per coulomb. It's the amount of joules for every coulomb of charge. And it's just a shortcut that allows us to do just like we do at the bulk barn. It allows us to say, okay, I don't know how many kilograms I am going to get, but I know if I multiply them by 150, it'll be the price. Here, we don't know how many coulombs we're going to put here. But if we know what the price is, or the voltage, then that means I can figure out what it would be by using this multiplication. I just take my voltage and work it out. Okay? So, voltage is equal to the electrical energy per charge, unit of charge, E over Q. This is how we can calculate voltage. All right? Okay, now it gets a little bit trickier, because what we can do is we can look at voltages in different situations, right? So we can go back to where we had our little idea of electrical energy. Let's take a positive charge here. It's making a field, right? In blue, I'll draw the field. This is the field that it would draw, it would make. And now I'm doing one that's opposite gravity, because by now we can understand that. All right, so let's say I take a spot, and I say, what about this spot right here? Here's my spot. I might want to know, what's the voltage at that spot? In other words, if I were to put coulombs of charge there, could you tell me what the joules for each coulomb would be? And so the way we figure that out is we consider that voltage is the energy per unit of charge. Now, we're going to call this the charge. This is the test charge we're putting in there. So we'll keep the little t for test. Not the red charge that's making the field. That's the master charge, the positive red charge in the middle. Now, that means that this is equal to K, Q1, Q2, or Qm and Q test. Those are the two charges. And the distance between them are divided by Qt, the test charge. That should be a subscript T. Let me fix that. Subscript T. Well, what does this simplify to? Well, essentially, if you're dividing by Qt, you're just dividing out this term. And so we end up with the voltage at this particular spot is K Qm over R. And so what that means is R is how far away it is. And all we have to know is what the master charge is, the red charge. If I knew that was something, I could figure out the joules per coulomb at that particular spot, and I would be able to then multiply it by any other amount of charge to figure out what was going to happen there. So what we say when we talk about voltage is we mean, let's say it came out to 8 volts. Let's just say What 8 volts means is it means that it would take 8 joules for every coulomb that you drop in this spot. Right? There would be 8 joules of energy for every coulomb that you drop in that spot. So that's what volts means. It's joules per coulomb. And it's a little bit tricky to get your head around. But once you sort of think about the bulk barn and how that works, you kind of get the idea. Okay, one more thing with voltage. You'll recall that with parallel plates, we could set up a situation where work, or electrical energy, same thing, change in energy, is equal to QED. And D is how far apart the plates are. Right? Okay. Or basically how far you would move. So now, if we take this equation and we want to turn it into voltage, we would simply divide by Q. Because voltage is energy over charge. So what we get is the voltage is equal to QED over Q, which cancels, and we get that the voltage is simply equal to the electric field strength times the D. And D is the distance between the two plates. So for parallel plates, we can shortcut voltage even more with this equation right here. Okay, so what I'm going to do now is prepare another video, and I'm going to show you all the different equations and try to give you some perspective